So now we're starting our conversation on the very last part of the entire unit on electromagnetism, which is the oscilloscope. So the oscilloscope looks somewhat like this. This is a rough depiction of what this looks like. So you have two important dials here. One of these is called the time base, another one is called the Y gain. And what the oscilloscope basically enables us to do is that it allows us to look at voltage signals. Now with DC, it's obviously not very useful because DC is just the same voltage all throughout, it doesn't change with time. But with AC signals, it's really useful. So for example, in our syllabus, we just look at this very simple type of voltage signal, but there are also many other types of voltage signals in reality. For example, you have something like this, you have some like this as well. So the oscilloscope allows us to look at that and analyze those waveforms. So this is used to represent voltage signals. The two important dials are the time base and the Y gain. So what the time base tells us is that it tells us what time each horizontal division is equal to. So for example, on this display that you can see here, this is 1 centimeters, this is 1 centimeters. And for example, if this is set to 1 milliseconds per centimeter, horizontally it tells us what 1 centimeter, so what one division is equal to in terms of time. So you can imagine that when we are talking about this oscilloscope, this is basically just a graph of voltage on the y-axis and time on the x-axis. So basically here what we have is this idea that we'll be able to analyze this voltage signal. So the time base just tells us that what time each horizontal division is equal to, right? So for example, if you have a time base of 5 milliseconds per centimeter, this means that every division on the horizontal axis is equal to 5 milliseconds, right? So that's the idea here. Now for the time period, you just have a very basic formula that you need to know. And it's not even a formula as such, it's just a unitary method. So basically, if you know that if every division is equal to 5 milliseconds, so it makes sense that for the total time period, you would just multiply by the number of divisions. And because I've studied waves and because I've studied AC signals as well. So for example, two, three, four, five, six divisions. So if I know that each division is equal to 5 milliseconds, I would just multiply by the number of divisions to get the total time period. So the way I write this formula is that the time period is the time base, or what is also called the time base setting, multiplied by the horizontal divisions that correspond to one wave. And we'll be doing an example as well shortly, so all of your doubts would be cleared. And for frequency, obviously, if I have the time period for the frequency, I can just use this formula that I saw way back when we were talking about waves. Now what would happen if the time base is increased? So if I basically work this dial up to higher and higher settings, what would happen then? So as you can see, in this case, for example, the time period would turn out to be 30 milliseconds, right? Same wave. So if I need less divisions, then for example, if it goes from 1 to 2, so if the time base has doubled, then I only need now, for example, if previously I need 1, 2, 3, 4, 5, 6 divisions, 30 milliseconds. So now because each one is worth, okay, so my bad. So that was according to 5, right? So for example, if it goes from 5 to 10, so then I would only need 3 divisions for that entire wave. In that case, the wave would just be like this. So you can see that horizontally it gets compressed. So the wave shape compresses horizontally, and similarly if the time base is decreased, then it would expand horizontally. So this is an important idea to understand. So if time base increases, and if it's the same time period, then obviously the number of horizontal divisions needed would reduce. All right. The other setting is called the Y gain, which tells us what voltage each vertical division represents. So as we had the time base for the horizontal axis, we have the Y gain for the vertical axis. And just for clarity, let me also make these lines. They are not really there on the oscilloscope, but this is rather to show the quantities that are, basically it's understood that these are the quantities which are there, right? So voltage on the y-axis, time on the x-axis. So now what the Y gain tells us is what each division is equal to. For example, right now, if this is set to 2 volts per centimeter, so this means that this is 2 volts, so this would be 4 and this would be 6 volts, right? So again, it's the same idea. For example, a Y gain of 0.5 volts per centimeter means that each vertical division is equal to 0.5 volts. So again, if each is equal to 0.5 volts, I just multiply by the number of vertical divisions to get the amplitude of the voltage signal. So it's just equal to the Y gain multiplied by the vertical divisions that correspond to the amplitude, because I need to find the amplitude. And just as I had the wave, for that I know that this is what one time period looks like, right? So similarly, vertically, this is what the amplitude looks like. So I just multiply by the corresponding number of divisions. If the Y gain is increased, it's pretty much the same idea. Now each division is worth more volts, right? So if each division is worth more volts, obviously I need less of those divisions to represent the same amplitude. In terms of this formula, if I increase the Y gain, then I need less vertical divisions if the amplitude is the same. So then the wave shape again compresses in the vertical direction if the Y gain is increased, and vice versa. For the signal shown in the diagram above, calculate the time period, frequency, amplitude of AC voltage. Okay, so for the time period, again I can see that the time base is set to 1, and this is 1, 2, 3, 4, 5, 6 divisions. So for the time period, I can just use this formula. So 1 milliseconds per centimeter, and also look at how I write it. Because the way I write it, I've never had to memorize this once in my life. So time period is 1 milliseconds per centimeter multiplied by 6 centimeters. So I can see that, yeah, this is actually time. This is 6 milliseconds. Part B, I have to find the frequency. So frequency is 1 over time period. So that is 1 over 6 milliseconds. So I just plug these numbers into my calculator. So this turns out to be 166.66, so 167 Hertz to 3SF. Amplitude, for that I'll need the Y gain. So Y gain is given as 2 volts per centimeter. Again, if I'm smart enough, I don't even really need the formula. So 2 volts per centimeter, this is 1, 2, 3. So it's 3 divisions. I can already see it's 6 volts. But if anybody really insists on using the formula, let's do that. And I'll also write that the same way. So amplitude is Y gain, which was 2 volts per centimeter multiplied by the divisions corresponding to the amplitude, which were 3. Again, these cancel out and you very comfortably see you get 6 volts through this as well. Okay, the time base is halved and the Y gain is doubled. Draw the new wave seen on the CRO. Now, if the time base is halved, then the horizontal divisions required for one wave would double, right? They're inversely proportional. So if time base halves, I'd need more. So if I have two waves here, in this case, I would only have one wave now. So what it would look like is this and this, right? So the time base is halved, so each division is worth less. So I need more divisions to make the same wave. But then we also have something for the Y gain. So Y gain is doubled. So if Y gain is doubled, then I need less, or precisely half the number of vertical divisions. So I know that how my graph is going to look like. If previously it was taking up 3 boxes, now it's only going to be 1.5. And if anybody is such a lover of the formula, for the lack of a better word, you can also do this using the formula. For example, with the Y gain, I know that the amplitude is 6, right? So if the Y gain is doubled, if it goes from, 2 to if it goes to 4, multiplied by the divisions, so the divisions would be 1.5, right? 6 over 4 is 1.5. That's the same thing we see. So then what this graph looks like is going to be like this. So yeah, precisely like this, halfway, and then the other way like this. And yeah, this is also supposed to be halfway, exactly how it's drawn, right? So this is how the time base and its settings work. One last idea here is regarding the different voltages then that can be shown and whether the time base is on or off. So for DC voltage, we know that it doesn't fluctuate between any values. It's the same value throughout. So if the time base is off, as you saw, there are also knobs to have the settings on or off. So if you turn the time base off, what happens is that you have just one value of voltage, and that's how it's shown. Because the time base, what it basically does is it makes the trace move across the screen. So then when you turn the time base off, you have this, basically it's an electron beam, which moves really fast across the screen. So it basically becomes a line. So the time base is what makes it move across the screen. So then it basically just becomes a horizontal line like this. Similarly, with the AC voltage, for example, if it's an AC voltage, I know that sometimes the value is +5, other times it's -5, +5, -5. Again, if the time base is off, so it's not going to move across the screen. So it just looks a horizontal line like this. But then when I do actually apply the time base is what gives me the sine shape. So that could possibly be looking like this. Alright, so that's the idea of the oscilloscope, and this finishes off the entire unit on electromagnetism. So this is great if you want to revise. So yeah, that's something that I hope would help students from my side. If you guys have any suggestions, questions, or anything at all that you want to discuss or need help with, feel free to drop a comment, like this video, share it with your friends, whoever may benefit, and I'll see you in the next one. Take care and bye.